Yeah, today a webinar about the self-cleaning heat exchanger, and a technology by Klaren International. But maybe to first say something up front. Let me go to the next slide. Who are we? Klaren International is a Dutch engineering and technology company. So we are a team of engineers and based on both process and mechanical engineers. We are based in the Netherlands, but since a few years we already also have a base in India, because this is for us an important market. As Klaren International, we are part of the Taprogge group, and Taprogge is a company, a German-based company, active also in the cleaning of heat exchangers, what in fact our technology is also about. They are world market leader on this sponge ball condenser cleaning system. So a cleaning system specifically aimed at aqueous liquids, mostly waters like seawater, river water, where the fouling problem is in fact about a combination of scaling and also biological fouling. So we became part of this group a couple of years ago, but still our focus is on putting the self-cleaning heat exchanger technology into the market, which is based on the fluidized bed. But I will tell you a lot about that later. As an engineering company, we work together in a network of specialists. So we don't have all the specialists in-house, but we have a network of people around us that assist us in the detailed engineering, like for example CFD work as one of the examples. So we design and engineer, but it's also important to note that in all cases we will also do the commissioning, because at the end it's very important after the designing and having things built that the installation is properly commissioned, and also that the parameters are as per the design spec. If it comes to manufacturing, we would outsource the manufacturing, because manufacturing is really a specialty. We always talk about pressure equipment, and for pressure equipment you have a lot of codes and legislations, and of course it's an art. We work together with reputable firms that can manufacture the components for us, but they do this on the basis of our engineering spec, and we will also follow the manufacturing, because at the end it is the quality that we are looking for. And this is also something which I would like to say up front. Our aim is, our value is that at the end the customer is happy. So it's not that we only want to sell the equipment. Of course we want to do that, but we only feel happy when at the end the client is happy, that the client has reached the performance, that the client has got let's say the away from the fouling problem, and has just a heat exchanger that is working, and that is working with a constant capacity. Because this is exactly what the topic that we are talking about today. Solving fouling as a major problem in industry, as a major problem in heat transfer. And at the beginning of such presentations, of course, always nice to show some dirty pictures. These pictures, in fact, show real cases that we are working with, or that we have been working with, and that, of course, shows a range of fouling cases that differs based on industry, based on application. But always you will see that a heat exchanger will start with a clean surface, nice heat transfer, good capacity, good heat duty, but at the end that this layer is formed on the heat transfer surface, and this layer will block heat transfer, which at the end will mean that you lose capacity, or, because as an engineer you can also already during design take fouling into account, you can oversize your heat exchanger and thereby increasing your heat transfer area, and you can delay the moment and at which your capacity of the heat exchanger will go down. After this moment there will be loss of energy, which of course is a negative thing. Fouling could, in that sense, also lead to production losses, or could lead to a reduced operating capacity. Later, I will show you the example of an evaporator, but there we really see that within days or within some weeks, the evaporation capacity can go down with a factor of 50%. So that means you buy something for a capacity of X, and at the end you only get half X. So of course there is a benefit if you can solve this. Another negative thing about fouling is that at the end, these heat exchangers need to be cleaned. Cleaning can be done by chemical means, for example with acid flushing, or by mechanical means, and then you have to open the heat exchanger, and by high pressure water jetting you need to clean the tubes. This sometimes can be easy. Well, what is easy? But recently we have seen that even cleaning a 31 tube unit took 4 days for that the heat exchanger tubes in fact were clean, because this layer was so sticking to the tube wall and was so hard that the high pressure jet had really difficulty in removing it. So we should not take it too light, and there's really interest in solving this issue. And that is exactly what our technology is doing. So let's just directly jump to the core of our technology and to explain you this. In this slide, you will see an animation. Yeah, sometimes it will start and sometimes it will stop, but you will definitely get a feel of how the technology is working. So in the core of our technology, we add cleaning particles to the fouling liquid, to the process liquid that gives fouling. So that can be an aqueous liquid, that can be an organic liquid, that can be oil, that can be several types of media. But we add these cleaning particles up front of the heat exchanger. And then so that's at the bottom of the heat exchanger, and maybe already directly good to mention that the heat exchanger is a vertical heat exchanger, and that will be always the case. So that's also a handicap. A question we always get is, can you also do it in a horizontal heat exchanger? Well, that will be hard or impossible, because we need the direction of gravitation to have a good fluidization. Because after we have supplied the particles into the inlet channel, they are taken with the upward flow and will pass through the heat exchangers, through the heat exchanger tubes. And effectively, the flow is faster than the falling velocity of the particles. So the particles are taking outward of the heat exchanger, then are passed through a particle separator, where we take out the particles, we separate them from the liquid, and then the particles are recirculated back to the inlet via what we call the downcomer. So in our system, there is a continuous recirculation of cleaning particles. How does this cleaning mechanism then look like? Well, then we should zoom into what you can see at the left side in the circle, where you see that in fact you see the cleaning particles, and with the arrows you can see the movement. That gives an indication of the movement. So those particles really, let's say, they move in a chaotic way, and in this chaotic way, they will impact each other. They will also keep each other clean, but they will also give a light impact to the tube wall. And it is these very light impacts that give a continuously cleaning mechanism. The impact of the particles is what we call it gives a scoring action. And this scoring action is in fact the mechanism to keep the heat exchanger clean. So that's also what we say, that we have to continuously remove the developing layer faster than that it can develop, such that the net effect is that the heat exchanger remains clean. I already see a question popping up with some components, and how will this work in a revamp? I will come to that later. But your question is noted. So the particles are separated in the separator. We can use different mechanisms for that. That will depend on the liquid of the client. We can go for a sieve separation, or we can apply a gravity separator. A third option is a cyclone, but we're not so in favor of that because of erosion of the cyclone itself. What I also should point out, it's a continuous system. Because the removal mechanism is light, meaning that we continuously need it to keep the heat exchanger clean. But it's also because we run at a completely different tube velocity than what you would normally have in a shell and tube heat exchanger. Because normally in a well-designed shell and tube heat exchanger, and especially for fouling conditions, the tube velocity should be, well, at least above 2 meters per second, but we sometimes now even see designs of over 3 meters per second. These are not the velocities that we can work with, because that would give erosion, but that would also give a huge particle transport. So we run at lower velocities. But at these lower velocities, you would normally also have a lower heat transfer coefficient. But since we have the particles, in fact, this, let's say, negative effect on the heat transfer is compensated, and sometimes even more than compensated, by the action of the fluidized bed itself. So the fluidized bed will improve the heat transfer. If you now compare apples to apples, so shell and tube with high velocities versus our technology, lower velocities but with a fluidized bed, we are on the same, let's say, magnitude of heat transfer. Of course, with the main benefit that this heat transfer coefficient remains constant over time. So our system, the cleaning mechanism by the fluidized bed, works continuously, and it's not an intermittent process, because the fluidized bed is in the core of the cleaning, but also in the core of the heat transfer. So the fluidized bed has as a positive effect, well, it keeps the heat exchanger clean, it improves heat transfer, but the third also positive effect, which I also should mention, is that if you have a slurry, and I see that one of the questions is also about that, if you have a slurry with a high viscosity, then these type of slurries will, let's say, what they call exhibit non-Newtonian behavior. And that means that this viscosity of this slurry you can influence by shear. And effectively, our particles create this shear. So inside the heat exchanger, we reduce the viscosity of a slurry, and we would, in fact, improve already by only viscosity, improve heat transfer, but also make things better pumpable. So that's the third positive effect of the technology. And then, of course, the question we always get, and I also see it popping up now, is, oh, but if the particles clean the tube wall, will they at the end also erode the tube wall? So will we get problems with leakages, or do we need to replace tubes? Well, we know from long-term experience that the particles will not give erosion inside the tubes of the heat exchanger. So for long-term experience, I never had a tube to be replaced by had to be replaced because there was erosion of the tube wall itself. So the cleaning mechanism is really light, and that's maybe also a good thing to note, is that suppose you would already have a dirty heat exchanger, can this technology then also remove a layer that is already there? Well, that's not always the case, and that is a strong evidence that also the cleaning mechanism is not so aggressive that it will erode the tube wall. So coming to the next slide, in the next slide we will show a short video, and this video is of a demo unit which we have in our laboratory. This demo unit is in fact a heat exchanger, vertical with 31 tubes, but it does not have a shell. So it's only the tubes, and the tubes are made from transparent material so that we really can observe the flow conditions in the heat exchanger. We use that to optimize some things in our technology, but mostly also for demo purposes when we have clients visiting. But I will show you now the video. So this is the vertical bundle. At the bottom, you see the section where we introduce the cleaning particles into the tubes. In fact, you see that here. You see this. So you already see that there's motion of the particles. The cleaning particles moving upward in the tube. Here you see them flowing upwards through the tubes. And then at the end, they are going to the outlet channel. In this case, they go vertically upward in a 180-degree bend. That's not always the case. That depends on the particle separator. And here on the right side, you see the downcomer where the particles move downward again. It's like this sausage of cleaning particles moving from the top to the bottom towards the inlet channel. This video can also be seen on YouTube. And if you want to later have a look at it as well. What is also important that our technology, in fact, can work at all temperatures and pressures. The temperature and pressure is more relevant to the design of the heat exchanger, to the design of the pressure body, than it is relevant for our fluidized bed technology. So as long as it is a liquid, this technology can work. Of course, you can also have situations where there would be boiling, where there would be phase transfer. This is something which we normally would not recommend in our system, but in fact, we're working also on that to see if we can, to some extent, allow that as well. Okay, I go to the next slide, because what is important is what type of particles do we use? Well, the particles, the cleaning particles that we use in our systems are made either of two, in fact, could be three materials, but the third one would be glass, but we almost never use that. But the mostly applied materials will be ceramics, spherical ceramic particles, or it will be particles which we call chopped metal wire. So particles made from stainless steel or any other metal material. But it will not be a spherical particle because that would be too expensive and that would not, let's say, fit in the client business case. But a very good commercial attractive alternative is chopped metal wire, which is in fact a material which is used for blasting purposes. After that, these particles have been given a surface finish to take out to take off the sharp edges. We can use them in our system. So those two types of particles can be used, and they both have their own effect on let's say, the type of removal, or the type of removal, or you can also maybe say the aggressiveness of the removal. With only one real reason is that the removal mechanism is based on small impacts between the cleaning particles and the wall. And of course, the impact of these particles, of course, is linked to the kinetic energy of the particle. And in that, you will see that it's also the mass of the particle which is relevant, and that's linked to the density. And ceramics have about half of the density as the metal wire particles. In terms of size, you will see that typically we use particles with a size of between 2 and 4 millimeter. This also depends a bit on the tube size, because the particles on average has to be a factor of 10 smaller than the tube size, with only one reason, that is to have a proper fluidization of the fluidized bed inside the tube. Why is the cleaning particle and the size and also the volume fraction important? Because at the end, in the heat exchanger, there will be a continuous, let's say, a continuation of the deposition. We don't change the reason why there is fouling. No, we only remove it with just a bit faster than that it can develop, and then the net effect will be that the tube remains clean. So that also means that if you have a fouling case that is very severe and very fast, we need to have a faster removal mechanism, a faster cleaning mechanism. And we can influence that, for example, by taking a bit higher volume fraction of particles in the tubes, or maybe taking a bit larger particle, or taking a more heavy particle. That's the way we can a bit play with the system. And if upfront of a new client case we say, okay, this is an application we do not really know, and it could also be that we suggest to first do a test with our technology. And we just completed a test at one of the clients with edible oils to prove that we have the right combination of particle material, particle size, and volume fraction, so that we can really upfront say, okay, for these conditions, we can reach up to zero fouling, because at the end, that is our aim. Of course, at the end, then when our system is installed, when the fluidized bed system is active and there is no zero fouling, then of course there will be strong advantages if you compare it to the situation which I showed at the beginning of the presentation, where you see the pictures with fouling inside the heat exchanger. So by the zero fouling, of course, there will be an improved energy efficiency, increased availability and production. In fact, it's just the opposite of what was earlier the disadvantage. But what is also good to mention is that in many cases, we can also reduce the pumping power requirements. Why? Well, because there are some things that contribute to that. We use a lower tube velocity. And of course, the pressure drop in a tube, it will always be proportional to the velocity squared. So if you reduce that velocity with a factor of 3, then you can imagine that the square will give you a significant reduction. But there's also a second thing. If you would, and that's today, we cannot go to that detail, but if you look to the design of a heat exchanger, then you can easily, let's say, derive that the length of the tube that you require for a certain temperature increase, so let's say from 5 to 10 degrees, so the length that you require to get from 5 to 10 is proportional to the liquid velocity. So that also means that you need a shorter tube, so a shorter tube length. So in some cases where you would, in a conventional heat exchanger, use a 3-pass system, our technology can do with a single pass. And in fact, we also need a single pass for correct fluidization. So a lower tube velocity in combination with a lower tube length, at the end, will give a reduction of the pressure drop. On the other hand, we do need part of this pressure drop to lift our particles. So part of this effect will be taken by the pressure drop that we need to lift the particles. And this pressure drop will depend on the volume fraction that we have in the system, will depend on the density that we have chosen for the particle materials, and of course the tube length itself. But the net effect in many cases is that the overall pressure drop reduces. Well, I just see a small question popping up, but I can answer that immediately. If you would listen to, oh, sorry for this. If you would listen to our technology, to the heat exchanger itself, you will hear a soft flistering noise, but it's definitely not a heavy noise. And sometimes you even have to ask if people can be quiet if you want to listen to it, just to detect if everything is working fine. Yeah, so the technology in itself will definitely have a very positive advantage if upfront you start, of course, with a fouling case. So what we also see, if a client says, yeah, I need to clean it once per year, yeah, then in most cases there will not be a real business case to go to our technology. There has to be a driver for the technology, because it will require an additional investment in equipment, but also in cleaning particles. Yeah, a question which is also on the list, and which I think is very relevant, and I also want to, let's say, to pay some attention to this, is can you apply the technology when the heat exchanger is already there? Which is of course a very relevant question, because clients or users have invested in equipment, and then of course if you cannot reuse it, well, that would be let's say the divestment, which is of course not beneficial. So of course it is good to look at, can we revamp, can we retrofit an existing system? And upfront, I want to stress that this is possible, but not always. And we always will have to look from it from the engineering perspective, because at the end, what I don't want is that we do a retrofit and the performance is not as what it should be. Let's say we will only grant a retrofit or perform a retrofit when we believe that we can match the performance, but in most cases that we can exceed the performance. So it will always require what we call a feasibility study. That does not need to be a lengthy effect, but or a lengthy exercise, but we need to carefully look at it. Of course, the starting point is the available heat exchanger bundle. The starting point is that you have to maintain the heat duty. Heat duty is, of course, a direct requirement from your process, or for an evaporator, it's a direct requirement for how much evaporation you want. Preferably, we would like to use the existing pumps, if that's possible, and of course, it has to fit within the available space. Which is also a logical one. And just to give you an example of how this has worked out for an evaporator, and you see that on the right side of this slide, is before the revamp, you see a forced circulation evaporator. So just to explain you, it starts with the pump on the bottom left side, and then the duct goes upwards into this single pass heat exchanger bundle. It then goes to the outlet, and from the outlet the liquid is flushed into the vapor liquid separator, so the pink vessel on the top, and after flushing the liquid is returned to the pump, so a forced circulation evaporator system. In fact, in this case, we also assessed if we could retrofit this, and this is possible. At this moment, the commercial discussions are ongoing, and what we need to do for that. So we first assessed if thermally it was possible. Well, based on new flow conditions, but with an additional or with a higher temperature rise over the tube, it was possible to maintain the same heat transfer coefficient, or sorry, to remain the same heat duty with a better heat transfer coefficient. So also the heat exchanger would now have an over design. So thermally it was possible, and then of course the main question was also, is it possible in terms of layout? Well, we were lucky because in this case the space between the calandria and the vapor liquid separator was large enough. If you can see it's on the top side to fit in this particle separator. So based on the space, it was also possible. The only question mark in this case was if the existing pump would be the best match, because of course we can reduce the RPM of this actual flow pump, but then it gets to, let's say, a part of the flow curve which is less in efficiency. But also an actual flow pump is a nice pump, but let's say for some pressure drop, it does not have this very good efficiency. So in this case, we gave the recommendation to look at a change of the pump, which would earn itself back within 2 years, based on a lower energy consumption. So yes, a revamp is possible in some cases, but it always requires some engineering effort. Then coming to where can you apply the Klaren system? In what type of industries or application? Well, in fact, that is numerous, and I see also that I have to watch time a bit. We have had many applications in the past, so not within Klaren International, but our inventor has had many applications in different kinds of industries. So that ranges from heat exchangers that are used to cool geothermal brines. We had an application in the crude oil, or in a preheater for crude oil. I must say this is a difficult area for us because refineries always have horizontal arrangement of heat exchangers, and the plant people really, they are, let's say, in charge of the arrangement. So at this moment, there's no willingness to consider a vertical arrangement, which is a pity because a lot of energy could be saved there. We have had applications in the paper industry, reboilers in the chemical industry. I will show you an example later on as well. Evaporators, definitely a strong market area for our company. Seawater coolers. We had pilot units in the mining industry. But I should also mention that the formation of ice is in fact also the same mechanism as the formation of a fouling layer. So you have freezing, you have the formation of crystals on your heat exchanger wall, and the fluidized bed has the same effect of on ice formation as it has on another fouling layer. So also our system is able, within some limits, I must say, because sometimes deposition will just go too fast, but within limits, we are able to keep a heat exchanger clean from the formation of ice. Let me get one sip of water. So this whole list now converted in some real examples. 3 of them I will discuss in detail after this slide. But the right bottom or the right top is only on this slide, and this is a heat exchanger which is in fact based on the first arrangement of our technology, I would say. And this is internal circulation. And the picture which I've shown you before, as to explain when I explain the technology, you see this downcomer outside the heat exchanger bundle. This is what we call external circulation. But initially, but that's really more than 20 years ago, our inventor started with providing this system with internal circulation, which has some drawbacks, but it definitely had the same cleaning effect, because you can also see that this was a client that had to clean the heat exchanger more than once per week. After installing the technology, there were no cleanings anymore within the year. They opened it once per year for a maintenance inspection, but that was about it. In this case, it was a chemical liquid, but also which gave to kind of sticky layer, sticky fouling layer, also for this sticky waxy deposit, the heat exchanger or the technology, the fluidized bed technology, was able to keep the heat exchanger clean. Then on the left side, you see 2 evaporator examples. I will tell you more in detail about it later. And the right bottom, you see an application for, not an evaporator, but a normal heat exchanger. In this case, in the zinc phosphate industry. And this was realized in Turkey. The left top was in India and the left bottom was in Japan. But more details in the slides to come. One of the examples shown was an evaporator plant in India. And this evaporator plant was for a company that manufactures dyes for the textile industry. They had a multi-effect evaporator plant consisting of 4 effects, where the majority of their fouling issue was in the first effect. So it was in the effect where temperature is the highest. Concentration is not the highest because it was a forward feed, but the temperature of the tube hole was the highest, and the effluent contained calcium sulfate, which together with organics led to really significant fouling. And within I think within 10 days, the evaporator capacity reduced by half. So they came in contact with our technology via our partner in India, which is Sachi, and we came into discussion with them. And they also raised us the same question: Can you reuse the heat exchanger? Can you revamp our system? And at the end, we could. We showed the feasibility study to them. In this case, we were a bit lucky, and I want to say something about this. The reason is that the existing heat exchanger was a 3-pass system, and this 3-pass system run with a tube velocity of around 2.2 meters per second. So we wanted to reduce the tube velocity, so to around 0.6, 0.7, which is a factor 3. So then, if you would want to maintain the flow, you would need 3 times the number of tubes. Well, that was in this case easy because it was a 3-pass arrangement. So we took out the partition plates in the bottom bonnet and in the top bonnet. So we converted 3-pass to single pass. And at the same time, we could directly reduce the tube velocity with a factor of 3, making an ideal fit to our system. In this case, we talk about a heat exchanger with a shell diameter of just above 1 meter. It contained 373 tubes. And maybe that's good to emphasize because I did not mention that in the beginning, but our technology might maybe sound a bit simple. You add cleaning particles, they go over all the tubes. But of course, if you have 5 tubes or 7 tubes or 30 tubes, that might sound easy. But now in this case, it was 373 tubes. And the original inventors spent a lot of time in understanding this distribution mechanism. So we now really know how to design it such that all the tubes will see the same amount of cleaning particles. So we do not only clean the midsection, but it's really that all tubes will remain clean. Well, after installation, of course, we were very interested to see how the unit would perform because, as said, we retrofitted the first effect, but effect 2, 3, and 4 still also had some fouling, but were not converted because at the end, what I said already earlier, our technology does require an investment. Then it's better just to point or to install the cleaning mechanism where let's say the problem is the most. So in this case, the first effect. What you see in this graph with the blue triangles is the evaporation capacity as it was before the conversion. So on the y-axis you see the evaporation capacity, and on the x-axis you see the runtime. These are actual plant data, no data adjustment or corrections, really plant data, and they take the plant data on a daily average, where sometimes based on the level in vessels, there can be slight changes. So you also see that sometimes the points vary a bit, but on average you see that within 300 hours, we went from an evaporation capacity of 4 cube per hour to an evaporation capacity of just below 2 cube per hour. So a significant decrease. After the retrofit, and in this case, I only show you the first 900 hours. At this moment, we have more than 7,000 hours. Real operating hours in terms of calendar days, we're now approaching 2 years. You see that in these 900 hours that the evaporation capacity did show the daily fluctuations, but on average, the trend was neutral and the evaporation capacity remained constant. And a bit surprisingly, but also it appeared that the fouling in the second and third effect had reduced. The reason is not fully understood. We have some ideas, but of course this was a very nice, it was very beneficial because at the end the plant was not anymore cleaned in those 1.5 years. So was continuously running when it was needed, which of course was a very nice result, and also led to repetition orders with the same client. The next example is the heating of a zinc phosphate solution. So in the automotive industry, but also for some other metal parts, like for example steel in concrete, you require that the steel is coated before it's finally used. And in this case, the coating is done by a zinc phosphate solution, which in essence is a sticky material. And that's beneficial because that's when it attaches really nice to the metal. But it also has a downside, and the downside is that on the left bottom picture, you see these big baths where they put in the metal components. And of course, if you put the cool metal components in the bath will cool down. And that's why you need a continuously heater, or you need a heater to continuously keep the bath up to temperature. And in the heat exchanger that you apply, you will get that the zinc phosphate also starts to coat the heat exchanger. And because it's sticky in nature, every solid that you will have in this run-going liquid will deposit on the heat exchanger wall. We have installed this with a partner in Turkey at a provider of metal parts. It's quite a small unit made of SS304, running with ceramic particles in this case. And after installation, it really worked perfectly. But here I also want to say that we are open and transparent company. At this moment, it does show some fouling. And the reason is that the client has problems with the filter press, which is in between. So now they've just taken out the filter press. The liquid is continuously circulating with all those solids. And we see that now they need, once every 1 or 2 months, they need to clean the heat exchanger. But normally that would not be even possible because then it would be clogged within a day. So a nice example. On the other hand, we would like it to be better. The third example that I want to show you is a bit older, but it is relevant to mention it to you because the most asked question we get is, do the tube walls erode? I mentioned it in the beginning also earlier. And then we say, no, there's no tube erosion. Well, this plant shows that because this has titanium tubes. Titanium is not the hardest material, of only 1.2 millimeter in thickness. And in fact, the heat exchanger has run for 15 years before they changed the heat exchanger bundle. Then you can say, oh, but did they need to change it because of erosion? No, they changed it because, in fact, they didn't want to end up in this leakage problem. So just by preventive action, not supported by measurements of the thickness, they replaced it. But before, there was no leakage whatsoever. In this case, if it was also an evaporator, it was wastewater treatment from a soju distillation company. So soju is an alcoholic liquor, which is which is drunk in Japan. It's made from rice, and after distillation you get a wastewater that contains a lot of salts and organics, and gave a lot of fouling problems. They knew this up front, so they directly decided to install the self-cleaning heat exchanger. And this plant is still running in Japan with very good results. Yeah, so with this last application, I have come to the end of my presentation. Well, I'm happy that I managed to stick to the 45 minutes because sometimes I can take longer, but that gives also the room for questions as there are raised. Yeah, some of them I've already answered during the presentation. But definitely not all. So I will just open that screen a bit wider, such that I can see the questions. Are the cleaning particles food grade certified? Yeah, that's a good question. Yes, they are. We definitely have particles that are food grade certified. But we also must say that in terms of food, we are always a bit hesitant to say, yes, we can apply it. Because at the end, there could be some, let's say, metal erosion, dust in the system, because in the inlet channel and around the outlet channel, so not inside the heat exchanger tubes, but in the other components, there could be some light erosion. And of course, we don't want these things to end up in food. So with food, we are definitely a bit careful about where we can apply it and where we cannot apply it. Another question which I see is, can this technology be used for plate and frame type heat exchangers? Yeah, that would of course be very beneficial if it was possible, but plate and frame heat exchangers really run with plates that have a very small thickness or a small, let's say it's a spalt between the plates, and that can even go down to a couple of millimeters. So it's not possible to apply a fluidized bed there. And definitely also the direction or between the plates changes. So that would be very hard for us to do. We one time had a look at it in terms of development, but at this moment, no, we don't have such an application. Another question, and I think that is relevant for for crystallizers. I mean, of course, we are in contact with many clients that have fouling issues. So some of them already told us, well, what we tried is to put sand in the liquid, because sand also gives this scoring action. But of course that works to some extent, true. But of course, a particle or a sand material is maybe it's smaller than one millimeter. So the impact that it will give with the wall is more limited to what we have. So why would our cleaning particle do its job, and why would a salt crystal not do its job? Well, I think they both will do a job, but ours is more effective, and that's simply because the size is a bit larger, and that means that the large particle cannot follow all the turbulent fluctuations in the tube and will impact the tube with some velocity. And it's a small velocity component that will give this cleaning mechanism, where salt crystals might just give a too soft impact to really score the scale. Yeah, the question about noise, I already answered. So no, effectively the heat exchanger will not give an additional noise. If you would put your ear to the channel, you will definitely hear the action of the fluidized bed. But that's about it. Yeah, so there's also a question about some erosion in the partition plates. I'm not sure, because normally we have a single pass, so there are no partition plates, but some erosion in tube sheet and bonnets. The most erosion that we see, but really we have improved the system so that we really reduce this, is in the part what we call the inlet channel. So we redistribute the particles over all the tubes around the distribution nozzles, but we really have reduced that. So now we have opened the installation after 2 years, and we almost see no erosion there anymore. So erosion is really limited. There is also some erosion between the cleaning particles themselves. Maybe that is good to mention. So on average, the weight of the cleaning particles will reduce over time. And typically for the cut metal particles, we say that you have to take into account that between 3 and 5% of the volume will reduce in a year. But we also made some improvements there, so we're now closer to 3% than higher. But this is something definitely to take into account. Experience with separating cleaning balls from salt crystals. Yeah, that I think this also comes from the same area of let's say combining our heat exchanger with a crystallizer. This is also a topic of discussion with a partner that we have in Turkey, which really believes in this. I think there is no issue in separate, let's say separating cleaning balls from salt crystals, because we have particles which are a couple of millimeter and have a density of steel, so above 7,000, and salt will have a density of maybe 2,500, and it will be smaller than 1 millimeter. So based on our CFD work, which we know, the salt crystals will just leave from our particle separator if we have a gravity separator, and the cleaning particles will be separated towards the downcomer. What is the concentration of the cleaning particles? Yeah, that is a good question. So typically we see that for wastewater systems we run with a volume fraction of around 5%. If we really need to push heat transfer, then we can go to a volume percentage of 10% or just a little bit higher. normally not that much higher. In terms of clogging of the particle separator, we can say that if, for example, in wastewater systems, what we see is that everything is dirty, and you even have seen one of the pictures. So there will be not only cleaning particles, but even parts of scale layers that come from ducting, from piping, that pass through the system. So if we would use a particle separator with a sieve, then definitely for sure the sieve will get clogged, and then you introduce just a new problem. So there we see that it's better to use a particle separator based on gravity, and that has shown to really work fantastically. So that we can solve by that. Clogging of the downcomer, that could happen. I think I can remember one application in the past, which was in the paper industry, and there you saw that they closed the system down during the weekend. Then the system was stopped, so of course also the flow was stopped, and all the particles that were still coming into the particle separator went towards the downcomer. But then after that, also the small solids and fibers came down, and this was kind of a layer on top of these particles. And at the end, this layer over the weekend became harder, and it led to a problem in the downcomer. This was at the end solved by a different procedure to stop the unit. Other than that, we normally do not see that the downcomer can be clogged. Well, looking at time, I also think that I have to go to the end to come to finalization of this webinar. Is there maybe, Eric, a question that you say that needs to be answered at this moment in time, which is not answered yet?
Sorry, I had to switch on my mic. Well, I think most of them are answered. I think one thing, but already you also answered that this was about the revamp and how to connect the downcomer to that we add an inlet channel to connect the downcomer to the heat exchanger. So I think most of them are answered by now. Yes. If there is one final question, maybe, then please let us know now. Oh, one question, Marcus. How is the cleaning media replaced? How often?
Yeah, well, I already mentioned the weight loss that we can expect over the years. At the end, that does not lead that you need to exchange the complete set of cleaning particles. At the end, that could be possible, especially when you have a particle separator based on gravity, because at some moment in time the particles become too small for an effective separation. But that should not be faster than once per 8 or 10 years.
Okay, thanks. And maybe the first question from what was asked about the fluids and which type of fouling are typically handled by Klaren. We gave some examples of applications, but maybe more in general.
Yeah, well, what we see is a broad range of fluids. I think 70 or 80% of the application do, let's say, it contain a medium which is based on an aqueous medium, so with water and salt or other components. But we also have examples with oil, working on an application with edible oil. I've seen an application with crude oil. Yeah, so many fluids are possible, ranging from water to mining slurries.
Okay. All right, then Marco, thank you very much for this presentation. I want to tell everybody thank you for joining this webinar. And if you have any questions, please send us a separate email to webinar@klarenbv.com. And then we are happy to answer your questions. If there are any requests to have a one-on-one for a more concrete or discussion about a certain application or a certain case, then definitely we're happy to schedule a meeting one-on-one to have a further discussion and go more in detail about your question and the potential application you want to discuss about. So again, thank you very much for joining, and wish you a good day or a good evening, depending on where you are. And yeah, stay safe, stay healthy.